is, I'm just going to skip over it. But yes? Yes, so for self-avoiding walk, the kappa is 8/3. And for percolation, it is 6. Okay, so 8/3 is in the simple path case, and 6 is in the curve that hits itself case. I can tell you for if you take a uniform spanning tree, and you look at the boundary of that, that'll be a space-filling curve, which is SLE 8. But if you look at a single branch of the tree, that will be SLE 2. If you look at the easing model, it will be SLE 3. And there are a whole bunch of other models we know, these FK models, these different things where people in the physics side had related these curves to like central charge, computed their dimensions, Bertrand. I won't list all the physics names. There are a lot of people who worked on this. Yeah, so and once, you know, once Odette understood this on the math side, we could kind of go through and make the connection that, okay, this thing should correspond to this central charge, therefore it should be this, the same thing that, you know, just have studied in this sense. Okay. All right. So there's a version of radial SLE. I'm just going to gloss over this, but there's a version of where you grow to the center of the domain instead of having two boundary points, you have one point in the center, and the curve goes from the outside to the center. I'm just going to gloss over that. Here's a picture of one of these space-filling curves where it's drawn by color. So the color tells you the time at which it's hit. So it starts at red, and as the color changes, I trace through the whole curve. And so this is one of these space-filling curves, which if I just drew the curve, the whole thing, you would just see a blank color. So I changed the color as I went so you could tell what happened. And every time you see a gap where there's one color on one side, one on the other side, that means that I first filled up this, and then at a much later time in history, I filled up the other side. And when you see a subtle gap, like a slight change in hues, it means I filled this side, and then a little bit later, I filled the other side. And so all these places where it looks like, hey, maybe, you know, you weren't using enough of a spectrum of colors, maybe you only had 16 colors. No, we have a very fine resolution of colors, but it just means that I filled this in a slight later time I came and did the other side. And so this is one way of visualizing a space-filling curve. Okay. Now, random surfaces, here's a story. Just take some paper and make 12 squares. Okay. And now, imagine that you take out some glue, and you try to glue these squares together. For example, maybe I take this edge here, and I say I'm going to glue it to this edge here. Okay? Well, I have here 12 squares, 4 edges per square, which means 48 edges. Okay? So there's some finite number of ways to assign every edge one partner. Okay? And then I glue the partners in an orientation-preserving way, and I get an orientable surface, okay, or a closed surface. So after I glue, so there will be 24 gluings, and I make myself a surface, okay? And this is a picture that Bertrand made. He's here. So in math, you know, a lot of physics today, we do a lot of stuff on computer with simulations. But I think, you know, really the old school physicists, they really like to physically do something with their hands, right? You want to actually interact with the real world. So he said, I'm actually going to make one of these random triangulations. You know, he actually built one of these things. Here it is. Okay, so this was produced by someone from the younger generation who does things on computer. This is Mark Herr. He did it with a large number of, you can do it with quadrilaterals or triangles, but made a random surface and then put it into some software that would try to embed it in 3 space and show you what it looks like. And it looks something like this. Okay. So these were first studied by Tutt in the 60s. There are lots of variations. And, you know, you can think of these as random manifolds once you glue them together. And we know that this thing converges to the, in the limit, to the sphere. Or to a certain continuum object that we call the Brownian map. Okay. But for now, I just want to say, that you can make this surface and see what it looks like. And I have some other pictures. Okay, so for anyone who was lost before, wake up. It's movie time now. So this is these are made by Jeremy Bettinelli. And here's a picture of one of these planar maps. Okay, and you see it has this crazy wild fractal structure to it. Okay, they're very, very beautiful, these things. This here is just a, these were quadrangulations, yeah. You can do it with triangles. There are lots of variants. And you can see they're fractal. They have a lot of little narrow things sticking out of them. They don't look like your nice smooth manifolds that you're used to seeing. Okay, and the good thing about these pictures is that, so here's one that's a torus. It has a hole in it. The amazing thing about these pictures is that you already understand the math used to create these things perfectly. I just take a whole bunch of squares. There's a finite number of ways to glue the edges together. I look at that finite set. I pick an element out of that set uniformly at random and make a map. And then I plug it into a program that makes a picture. And that's it. Okay, so you understand this story perfectly, okay, for how these things are constructed. And they have this amazing structure to them. Well, yeah, that's right. So this isn't an exact, embedding. I mean, it's kind of, there's some software that, it breaks the rules when it has to try to make this thing look like a nice surface. But it gives you kind of a general sense of what these things look like. Yeah, that's right. So, this is giving you a rough sense of what these things look like. I mean, if you look at the triangles here, or they don't all look exactly the same shape in the picture. So the software is cheating a little bit. But they all look kind of roughly the same size. So it's giving you a rough sense of what these things look like. Yeah. Yeah, right. Yeah, even more. That's right. So when the place where it looks like roughly flat, that's because of this slight cheating. So what I want to say is that there are versions of these things where you put some statistical physics on this. Okay, so everyone in this room knows these things probably from the string theory story, where you ask, we want to have this surface embedded, in some higher dimensional space, your bosonic string theory or something. And you ask, well, what's the number of ways to embed a surface in a high dimensional space? Well, that's like the determinant of the Laplacian to some power. And so you just weight by that, and that will give you a different kind of random surface. And there was something that that physicists figured out early on, Polyakov and others, which is that somehow when you put a statistical physics model like an Ising model or a spanning tree or something, that should be morally the same as embedding the surface in a dimension with some value of c, where the c might not be an integer anymore, but you're weighting by the determinant of Laplacian to some power. Okay, and so you could kind of tune this parameter. And as you tune it, the surfaces become more fractal or less fractal, more tree-like or less tree-like. So the determinant of the Laplacian is the number of spanning trees of a graph. And graphs with very few spanning trees are just trees themselves. A tree has only one spanning tree. Okay, and so if I weight by something that makes me have a small number of spanning trees, that makes the thing more tree-like. Okay, the other direction makes it less tree-like. And so this parameter makes the surfaces more tree-like or less tree-like. And so the idea is that when you bed a surface in a high-dimensional space, it wants to be more tree-like. When you bed it in a low-dimensional space, it wants to be less tree-like. And then you can tune the parameters so that this C becomes even negative. And so you're making it even less tree-like than the versions I showed you here. So let me show you some pictures of this. This is like a Q-state Potts model with Q equals 0.5. So this is going to be smoother than the. Here's another picture of that same thing. This is something that's a little bit smoother than what you saw before. And let me show you something that's a little more tree-like. If I go down here and I do the one that corresponds to decorating by an easing model, this should be rougher. It's a little hard to tell sometimes, but it should be a little bit rougher, more tree-like than the yeah, it shouldn't make a difference in the limiting behavior. So I'm sort of mixing the two. Here's one. Here's one where you have a very high value of Q, so it starts to look much more like a tree. And that in the scaling limit, we would expect it to actually be a tree. Not. Yes, that's right. It can be anything, but I'm going beyond the bound. I mean, on the discrete level, Q can be anything. That's right. So above Q equals 4, we would expect that it would become, it would degenerate in some sense. It would maybe look just like a tree in the limit. Right. Okay. And here is a picture of what happens when you decorate by a bipolar orientation, which is something like putting it in dimension -7 or something. So this is this corresponds to something that's much more sphere-like than and all different kinds of statistical physics models, they all have some effect, but it should all correspond to this one parameter thing. They either make it more tree-like or less tree-like. This is something that's much less tree-like. Okay? All right, so all this is stuff that's, in some sense very much not new to physics, but in some sense, we're understanding it on the math side in lots of different ways. Okay. And, here's a picture where it's a map decorated by a pair of trees, a tree and a dual tree, embedded with a circle packing in the limit, and you get a certain structure. And the interface between the two curves is a certain space-filling curve. You can kind of draw this. So this is supposed to remind you of the picture you saw before of a space-filling curve. Okay, so sorry. I was trying to get away with skipping my explanation, but so this is a random quadrangulation. So these faces are quadrilaterals. It's embedded in a certain way that involves circle packings. So I add some extra edges, I do a circle packing, then I erase the circles, and you just see this quadrangulation. And the way it's done is there's a certain special tree that somehow, if when I connect the diagonals, I view every quadrilateral as an edge connecting this point to the diagonal on the other side. So there's a certain graph where I replace every quadrilateral with an edge, and then if I take a spanning tree of that graph, and this will be a branch of the tree, and if I don't include it, if there's a quadrilateral where I don't include this edge, then I'm going to draw a blue edge which goes the other direction, and that'll be like the dual tree. Okay, so it's a quadrangulation, but it's a special one because it has a tree and a dual tree pair. And I set up the boundary conditions in a certain way, so I have this, a red boundary branch and a blue boundary branch, and then there's a path that goes in between the two trees. That's a space-filling curve, and that space-filling curve, I can draw the colors, and looking at these colors, the space-filling curve is supposed to make you think of an SLE. Because it's some space-filling curve that looks, at least visually, kind of like the SLE curve I showed you. Okay. So now, important story when we try to understand these things. If I give you any two-dimensional surface, like, say, the boundary of the head of Michelangelo's David, okay, you can apply a conformal map that sends that surface to a sphere. Okay? And these pictures, they were made by David Gu, jointly with S.T. Yao at Harvard, I don't know, 20 years or so ago, when they really wanted to help people understand what Riemann uniformization was about. And they said, well, there's all this data with these classical works of Greek sculpture. Let's actually show you what happens when you map those. And so this is what happens. And it's a conformal map, meaning it locally preserves a right angle. If I draw a little right angle up here and map it down, it'll still be a right angle down here. And there's kind of a unique map that does this by the Riemann mapping theorem up to this, like, 3-parameter family. But once I fix a couple points, if I fix 3 points up here and tell you where they go, then it's determined. What's that? Yeah, right. You're not really seeing what's happening on the other side, right. So anyway, but the point of this is that if I give you any surface, I can map it to something flat. And this tells me that if I want to describe a random surface, one way to describe a random surface is just to describe a random, over on this side, when I map it over here, there will be a function, which I could maybe call rho, where the metric on this side is just e to the rho of z times the Euclidean metric. So rho is like the log of the area density over here. Okay? And if I choose a random function rho, then that gives me like a random surface. And so this is a different way. So I've given you two ways of giving a random surface. One is you do this story with the quadrangulations, and the other is you do this story with, you take some sort of a random function, okay, and define it this way. And okay, so it turns out if you take this function to be the Gaussian free field, okay, which I won't, it's been defined earlier in these talks. I won't redefine it here, but it's a certain random function. If you take this to be the Gaussian free field, then the surface you get becomes what we call this Liouville quantum gravity. So let me show you a picture of this, or it becomes a variant of it. Okay, so there are different flavors of how you set the boundary conditions. Whether you do it on a sphere, whatever. Remy talked about a lot of this in his talk, so I won't go all over that. But kind of the simplest version would be, just take the Gaussian free field, either on the whole plane or in some domain, and take e to the gamma times the free field, and where gamma is some parameter between 0 and 2, and then take here I've taken a box, and I've, yes? 2D is just it's a measure, Euclidean measure, say. Area measure. At this point, I'm not worrying about length. I'm just worrying about area. People worry about length too in this subject, but for now, just area. And so I just get an area measure here. And what I did in this picture is I broke this thing into squares that all have the same size in this area. Okay? So these all have the same size, which means I took this thing and I subdivided it into, I cut it into this, and I cut it again, and I kept dividing until I got to area less than delta for some fixed delta, and then I stopped subdividing. Okay, so every square here has area less than delta, but a dyadic variant has area more than delta, which means it's on the order of delta. So and you can see as gamma gets bigger, larger and larger gammas, the gap between the rich and the poor becomes larger. And so here you have some places where there's very little going on. So this is maybe middle of Iowa or the Sahara Desert, and here, maybe this is Paris and this is Manhattan. These are the population centers where everything happens. Okay, and those correspond to, everyone's been using the word multifractality, right? These are the special points where the field is larger than usual. Okay, and yes. 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 That's right. Is the conformal factor? Yeah, if you were doing this on a torus or something, then you would need one of those determinants. I mean, so part of what all this work that we've done in the last 20 years is really understanding why these different constructions are in fact equivalent. So the way, Polyakov originally explained it, it's maybe not immediately obvious that it's same as what I'm describing here, but in a sense it is. Okay, and there, Remy gave a little more details about how these things related in his talk. Yeah, that's right. So locally it's the same. If you want to do the global structure, then there are some subtleties that I'm not going to get into, but that Remy discussed. What's that? Yeah. Or what's the total area in the thing? That's right. So if you want to understand the total area, then you do need to think about. Oh, they're just coloring according to the size of the square. Yeah, well, somewhat they're related to the values of h. So if h is small, then the squares are going to be bigger because there will be less density. And if h is big, then the squares will be smaller. And so the gamma is fixed. Yes. Yeah, that's right. Yeah, that's right. Okay. So it's really just, e to the gamma h. And this is kind of the population density map for that. Okay. Now, random growth models, if I give you any graph, there's a natural story where I say assign every edge of the graph a random variable, maybe an exponential random variable, which tells you a new length for that edge. So I assign random lengths to these edges, and that gives me a random metric space. And I can do this on a grid. And here is a grid where what I did is I graph points according to their distance from the origin in this random metric space. This is called the Eden model, or first passage percolation. And so you see there's some roughness on the outside. Okay, this is supposed to correspond to these KPZ stories, the other KPZ, the Carrara-Parisi-Zhang, whereas the Liouville quantum gravity is the Knizhnik-Polyakov-Zamolodchikov KPZ. So these are different KPZs. Okay, and it's some kind of random shape. And but there's something else you can do, which is you imagine that at each time I'm growing this cluster, I pick a random edge on the boundary, and then I color blue the point opposite that edge. So I can imagine I just grow by this cluster of blues by just saying, pick a random point on the outside and add a new blue. Hey, this is like the easiest way to grow a cluster. I want to add a new point to it, so just pick a random place on the boundary and add a point there. Let it grow that way. That's like the simplest possible growth model. But then the second simplest thing you do is you would say, well, imagine this thing is a snowflake, and it's in a place where there's a very low density of moisture, and a little moisture particle comes wandering around from space, and it hits the first place that it collides with. Okay? And so, and when you do that, it's called DLA. And if instead you say it hits according to our harmonic measure to some power, then it's called DBM, or this dielectric breakdown model. Okay? And these things, dielectric breakdown model, DLA, they're things that, if you look at them, they're mostly studied by physicists, not by mathematicians, because they're too hard for mathematicians, mostly. But here's some simulations of these things. So these were introduced by Whit and Sander, physicists in the 80s. These are real-life pictures that are supposed to behave like them. Here I took this a few years ago, and I noticed, you Google this diffusion limited aggregation, and you get thousands of papers. By now it's more, maybe 20,000 papers, but you go and you look through, and I looked through the top 500, and only I think it was 4 of the top 500 were in math journals. And the rest were mostly physics, people doing simulations and studying variants of these things. And it's because in physics you can publish a paper by just doing the simulations and understanding what's going on. And in math you have to prove a theorem, and it's very hard to prove theorems about DLA, it turns out. There are very few theorems. Okay. So basic questions. Does this thing have a scaling limit? Is the shape random at large scales? Does the macroscopic shape look like a tree? What's the dimension of this thing asymptotically? These are all things we don't know. And then you could ask, what if you do DLA on a random planar map? Well, that's another question that I'll try to go. So now we get to the drama. And I'm going to do this quickly because I don't have tons of time here. But so if I what's that? I'll just use a few minutes. Have we passed? We started a little bit late, yes. Okay, I'll aim to do, I don't know, should I stop? We could take a vote. Who wants to see the drama? Okay, all right. So all right, okay. So I'll show the drama for 5 minutes, and then I'll be very fast about it. Okay. So the story is if you take a function, h, the Gaussian free field, and you take e to the I times h, that's a way of turning every value of h into an angle. So e to the I h is a unit vector. And if I just draw an arrow pointing that direction, this is like saying I view the value h as an angle, and I draw an arrow going that direction. And so now, and so if my h, if this is, this is h, it's a paraboloid. So h is x squared plus y squared, say. Then I draw the angles, it'll look like this. If I draw a flow line, it'll be some spirally thingy that goes around. Okay, and sort of the total amount of turning left keeps track of the amount h has gone up. So somehow the winding of this keeps track of the value of h. And I could, if I add a constant to h, it's like starting with a different initial direction. And so I get all these different angles. And so you ask, well, what if h is the Gaussian free field? And I try to do this. It turns out if h is the Gaussian free field, I take these curves at different starting angles, I get these wild lines like this, and these turns out to be these SLE curves, where the multiple of the Gaussian field I take determines the type of curve I get. Okay? And so this is something that maybe all physicists know, maybe not. Maybe not every physicist knows that if you take, every physicist knows that you can take e to the I times h, and that's called a vertex operator, and that it comes up somehow in conformal field theory. But they don't necessarily know that e to the I times h describes a vector field, and that the flow lines of this field are actually, in some sense, rays of a random geometry, and that they look like these SLE curves. Okay, so this is one of these stories of the last 20 years that we really like, and not everyone in physics knows about. Here's, if you add a log singularity at the origin, then what you get is sort of like a spiral of the curves starting at that point. Here I took all the curves starting going like in the northwest direction. The red curves all start going from the northeast direction. And what you find is that curves of going in different directions, they merge into each other. Okay, so if you were in a smooth world, they wouldn't merge, they would just get close to each other. But because h is not really a smooth function, it's this distribution, these curves merge into each other, and you get these trees of curves. Okay? So the fact that you construct these trees of curves from the Gaussian free field, that's another thing. We call these imaginary geometry curves. And so they're important, at least for my work, for us. And again, maybe not everyone in physics knows about these stories. There's another version where you take what we call the dual curves, which is where you look at the set of all points you can get to by just going in a north direction, in a northerly direction, say going northwest or northeast or something like that. And the set of all points you can reach turns out to be a curve that's like SLE kappa, where kappa and the original kappa are related by this kappa is 16 over the original kappa. And so you get these curves that hit themselves. Or for some gammas, you get actually space-filling objects. Okay? And it turns out that if you glue two Liouville quantum gravity random surfaces together, then the boundary between them becomes one of these SLE curves. Okay, so this is part of a long paper joint with Bertrand, the general story, that when you glue together surfaces, the interface between them becomes a curve. And if you glue together two of these space-filling trees, then what you get is a Liouville quantum gravity sphere, where the interface becomes an SLE curve. Okay? And this is one of the things where I think when I talk to physicists, every physicist in the world knew, in some sense, what these Liouville quantum gravity surfaces were. But they didn't necessarily know this general story that if you take two trees and you glue them together, that the interface between them is a space-filling curve. And moreover, if you vary how these trees are correlated with each other, so you make the two Brownian motions correlated with each other, then that varies the gamma. So if you make these highly correlated so that the two trees are essentially the same, then you glue them together, you just get a tree. It's as tree-like as possible. If you make them less correlated, then you get something where they like fit together in an alternate way like this. So it's like if I glue my hands together this way, I get a tree. But if I shift it slightly and glue them together, I get a sphere. And that's because when I shift, they become negatively correlated. And so generally, when these are, you can tune the parameter gamma just by tuning the correlation between these two trees. Okay, that's something. Anyhow, let me, very quickly, if I glue together two of these loop trees, I get a, the interface between them will be a curve that hits itself. And if I do these growth models on the trees, it turns out that if you take the right kind of growth model on the right kind of tree, we can really make sense of what happens in the limit. So we really know how to make sense of Liouville quantum gravity as a metric space and these growth models in a very precise way. And anyhow, I think I'll just end here. Okay, that's it.